Here's our course again. If we jump into this week's module, week 14, the live class resources from Wednesday's class are available and ready to rock and roll. They were made ready before the end of the day on Wednesday. We have the recording and resources. The Unit 5 self-assessment, the exponential function self-assessment is also now available. You do not need to necessarily start it right now, but I wanted to make sure it was available so you had to work on it. As the previous self-assessments, there's 3 questions. The first question is a free response question, demonstration of your understanding of the content. In this self-assessment, there are 2 parts. One part dealing with exponential growth and one part dealing with exponential decay. Each of these free response questions has a table, and then next rule, symbolic rule, and a question having to do with the context. For this free response question, the submission for these is a file upload. So just do your work on paper, or if you want to do your work in like Microsoft Word or a Google document, and add pictures into that, you can do that. However, the submission will be uploading your file, right? You're not going to type it directly into here for this question, for these 2 questions. Okay. If you want to do it on paper, take a picture and upload your picture. You can do that. If you want to do this in a Word document or a Google document, you can do that as well. Just make sure you're uploading those files as your submission. Okay. Question 2, once again, is the reflection on your learning. And question 3 is the actual self-assessment part where you pick where you believe your level of understanding is for this unit. It is important that the work you do up here for the free response questions is reflected in your self-assessment. Okay. If these questions are not done or you don't complete the questions, you can't give yourself a level of understanding of a 4. You didn't complete the work. If you're not sure what to do and you have to get lots of help, you might not be at a level 3, but you're probably at a level 2. You need to be fair with your self-assessment based on your ability to complete these questions. Okay. Any questions about the self-assessment? Okay, so then, good morning, Ariana. I want to show you guys that. You honestly might be able to do this after today's lesson. If you want to wait till after Wednesday's lesson, do that as well to start this. However, it is available. You can start it when you're ready. Great. And then again, there will be another session board for today. I'll review that at the end of our lesson. As always, I'll update the live class resources as soon as they are ready. So with that, if there's no questions, we're going to get started with our lesson today. We're going to look at a couple more examples of exponential decay. And hopefully they help further your understanding. So, yeah. So for example today, we're again looking at exponential decay. Okay. Our first example here is dealing with the drug insulin And this helps people with diabetes manage their blood sugar levels, people who are diabetic, people who need insulin, so that things don't go horribly wrong. After being injected, the amount of insulin in the blood reduces or decays by 5% every minute. So again, like last class, I was saying, we need to pay attention to the units of time so that we can answer questions appropriately. And then just as a reminder over here, we have our general form for our rule. Be the y equals a to the x. Right? We can also have exponential decay rules that are similar to our population growth or interest problems that we saw earlier last week. Right? Except in this case, we're using subtraction because we're losing a certain portion of value in the entire whole. Right? So these are the two general or exponential functions. A is our start value. B is the rate of change. All right, it could be the rate of decay, and it's always going to be the amount left over. Right? So if a ball rebounds to 3/4 of its previous height, 3/4 is the value of B. If a ball loses 1/4 of its height, right, the remaining amount is 3/4. B is 3/4. This is where this other formula comes in play. We're only told what is lost. We subtract that from the whole. This is 1 minus the portion lost. That's why we have these two different versions. Now, if we go back to our example, we have our drug insulin. It decays at a rate of 5% every minute. The rule here shortly. Our graph here helps model the breakdown of insulin in the bloodstream. So we have this graph. Our y-axis. Y shows the units of insulin in the bloodstream. And we have our exponential decay curve going down here. And then we have time on the x-axis in minutes. All right. So before we move on, based on this graph, what's the start value? How much insulin was given to this person who's being represented on this graph? And yes, definitely. It is. And how do you know it's 10? This, yes, it's on the y-axis. It's our y-intercept, right? So this is our start value. For this, based on what we were given in the context here, we know it decays by 5% every minute. If it's decaying by 5%, what amount is left over? What percentage of the insulin is left over after 1 minute? I've lost 5%. What percentage is left over? That's how many units of insulin will be left after 1 minute. Yes, Gatlin. But in general, what proportion, what percentage of the insulin is left over after 1 minute? Right, we were given this 5% here as the amount lost, right? The amount broken down. So what portion is left over? And is based on what we know, the amount that would be left after 1 minute. Because if we start with 100%, lose 5%, we're left with 95%. We have 95% left over. When setting up these rules, setting up these problems, we need to use the proportion of left, the fraction of things left over, the standard proportion, right? We'll use the number 0.95 when we get to writing our rule. These are equivalent. 95% is equal to 0.95 as a decimal. So, using the graph, estimate how long it will take for the units of insulin to break down in the bloodstream. In other words, when will the 5 units of insulin in the bloodstream? Right, so looking at the graph, estimate. When will we hit 5 units of insulin? At what time? How many minutes? Right, so let's look here. So 5 minutes, we're looking at our graph here. Each mark here is 3 minutes. Right, 15, 8. Right, so 5 minutes is going to be right about here. Follow that up to our graph. And then hit right about here. That's like maybe 7.5 units of insulin. 5 minutes doesn't quite get us there yet. Right, at 5 minutes, we're like, okay, 12. let's fill in the missing labels on our y-axis. This might help. Right? We look at y, right? It's only giving us every second. Right? We have 1, 2, 3, 4, 5, 6, 7, 9, 11 here. So 5 here. So 12. We're going to do here. This 5.8 ish. And then we get 15. That often thinks for 15. Yeah, 15, right? Then I follow that up. That goes along with that point there, actually. And we go over, and it's pretty much right there. Right? So we get 15 minutes. And that's just using our graph to estimate. We're given the graph, why not use it? Right? So we can say, approximately 15 minutes. All right? Again, there's a couple things going on here. One is understanding the context, and the other is understanding how to read the graph and interpret the context on the graph. Okay? The units is on the y-axis, units is insulin, our time is on the x-axis. Anything I can clarify for part A here? So then, part B, based on the provided information, we're given 20 units, a 10-unit injection of insulin, and insulin stays at a rate of 5% every minute. We want a symbolic function rule that can be used to model the pattern of decay from the graph. Right. Again, we want to find our rule that looks like this: y equals a times b dx. Right. Will be that start value. B is the rate of decay. That way. Let's see what's left. And in this case, x represents the number minutes. Right. And then we just need to fill this in. Replace A and B with their proper values. Y and X remain as variables. Y equals and something to the power of X. So we've already identified our start value using the graph, and it was provided again here as 10. What's our rate of decay based on what we talked about earlier? Much of this is left for each minute. And we have the 0.95 as the remaining portion, 95%. We lost 5% every minute. We get to keep 95%. in the parentheses here, we have 0.95. To the power of x. We will need clarification on how we got to the rule in this context. All right, so then we use the rule to calculate how long it takes for the insulin to break down. We've estimated it at 15 minutes already, so we're just going to use the value of x and see what number we get, right? 0.95 to the power of 16. For you. Later. When we put this in the calculator, we get 10 times 0.95 to the 16th power, you get 4.6329, blah, 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 blah. We'll approximate that at 4.63. Okay. So 15 minutes is actually like a little too much time. We went past 5. 5 was what we were looking for. So let's see what happens when we use 14. So 14, we're at 4.8767. So we'll round that to 4.88. But again, we're still not quite at 5. We'll find another one. Now, the reason we're using guess and check is because we will not learn the actual way to solve these for a unknown variable as far as an unknown exponent value until math 2, where you get what's called logarithms. You can use math 6. So we use guess and check. That's the best we can do. So at 13, we get 5.13. All right. So at some point between 13 and 14 minutes, we hit that halfway mark. We've lost half of it. We're left with 5 units of insulin. All right. All right. Now, this does not match our graph very well. Okay. And that's because if we look at the graph closely, we see that the actual dots or coordinates aren't on the line every time. Okay. The curve we have here, which is based on the function 10 from 0.95 to the power of x, is the closest we can get to matching these points. And these points are actual data points from insulin breakdown that were measured. And that curve is the closest approximation we can get. And to use the data point, it looks like 15 minutes. We had 5 units of insulin left. So using the function, it's going to be a little bit of a slightly different answer. Okay? This way they don't match up. Now, the last part, when we use decimals or fractions of minutes to get a more accurate estimate of how long it will take for the insulin to break down. Well, yes, we can. Right? There's no rule that says I can't use a decimal in the exponent spot. All right. Now we can get a better guess. I know that it's between 13 and 14. It's probably pretty close to the middle based on how far apart these two numbers are, 4.88 and 5.13. So we'll again use guess and check. This time we'll use 13.5. That's pretty darn close. We'll say that's about as close as we're going to get. We could have more decimals if we wanted. Try and get closer. Okay. Keep adding more decimals, right? Might get closer, but that doesn't really help enough. 13.5 is about as close as we need to get. We're at 5.00. It's pretty much right for 5.0. Right, so we can use decimals now in our exponents to get better approximations or better answers. Right? We get 13 and a half seconds, however you want to say it. Any questions on this example? This is the end of this example. All right. Next example. Here we have it. Suppose you just bought a new car for $25,750. On average, a new car will lose approximately 18% of its value every year for the first 6 years of ownership. Okay. So that means every year it loses 18% of its value. 82%, or 0.82, or the decimal, is how much of its value is left over. Right, we lost 18%, we get to keep 82%. So let's look at what happens to the value of your new car over the first 6 years of ownership. Based on the information we have, what is the start value of our car? What's the purchase price? Yes, just around 25,750. All right, and then if I multiply this by 2, right, I'll get my next number. We'll do that. And we're down to 21,115. And then multiply by 0.82 again. We get the value after 2 years of ownership. And that drops us in at 17,000. $314 and 30 cents. All right, and we continue multiplying by 0.82, represent the lost value for each year, right? How much value we get to retain. Then next year we're at 14,197, about 0.72. Right. Other thing you guys need to notice, your values in an exponential decay problem should be decreasing. If your values are increasing, you've done something wrong. Right? The numbers should not be getting bigger, they should be getting smaller. When you're doing your work, if your numbers are going the wrong direction, you probably made an error. All right, next year we have 11,642. $9,546. After 6 years, we're at 7,828. And 17. You bought for $25,750 is, after 6 years, only worth $7,828. It has lost a lot of its value. And that's just what happens when you buy a house. They consider the worst investments you can make because they usually don't retain their value. Then, what's the symbolic rule? And then now next rule. We know our start value. We know our rate of change. Write our rule. Right? Our symbolic rule will be y equals 1 at 5,750 and 0.82 to the power of x. The now next rule. Now 0.82. Next. There you go. Any questions so far? All right. Now, the last part of this problem here is more real life. Right? Let's suppose that you'd saved up $5,000 to help purchase your car and finance the rest over a 5-year period. This is a typical length of a loan is 5 years. Sometimes you'll do longer or shorter, depending. Good morning, Destiny. Depending on the situation and what type of payments you're looking for. That's all negotiated at the car dealership or with your bank. If you have superior credit, you qualified for a 0% interest rate on your financing. I just want to add the interest, compounded interest, and amortization to this example. That was more math. Now we're doing 0% interest. Based on this, your monthly payments will be $345.84. The question we're trying to answer based on our provided information is at what point in time will your car be worth more money than you owe? Right? The period of time where the car is worth less money than what you owe, which is assuming you get it off the lot, you're considered upside down on your loan. Meaning if you lose reason, it's in an accident and it's totaled, something happens, the value of the car will not cover how much money you owe on the car. Knowing when you're no longer upside down is actually a pretty good piece of information to have. You don't want to end up still having to pay for a car that you don't have. That sucks. So, this is the question we want to answer. We're going to use everything we've done so far, and this actually ends up using a linear function and an exponential function, so we get to get back into the previous unit, and that's kind of nice. So let's set up what we need. Now, in the original problem, we had a start value of 25,750 for our rule. We saved up $5,000, right? And use that to lessen the amount that we're financing, right? So our start value becomes different. Right? So our new start value is going to be the 25,750 minus your down payment. Okay, so that'll leave us with $20,750. Okay. This is the amount financed. This other note, the 25,000, is the value. That is our start value of the car. This is how much we finance. Now, typically, as soon as you drive a car off the lot, it loses between 20 and 30% of its value, right? That's considered over the first year, but as soon as you lose the car dealership, that car is not worth what you just purchased it for. How much value it loses within that first week of ownership depends on the car. That's just the way it is. Again, cars are horrible investments. So then, this is where we're starting at. So now, the amount of money we owe is a linear function. We pay $345.84 every month towards the loan of $20,750. Right? Over the course of 5 years, this should pay off our loan. Right? So we can set up the function for the amount of money we owe as a linear function. The money owed is equal to the amount financed $20,750 minus the monthly payment, which is our rate of change, $345.84 times X, where X is the number of months we've been making payments. Okay, so that's the money owed. Then we have the value of the car. That's the previous function. Right? Our value is determined by this depreciation, the exponential decay function. Right? Which is 25,750 0.82 the X power. So let's see what this looks like. what we're going to do is we're going to put both of these functions into test mode and see what happens. We have our linear function, 20,750 minus 145. $0.84, I think it was. Yep. Power. And our other function in here. And we can figure it out yet. We got to zoom way out for this. Wait, I need the y-axis. Turn back. There. So, we have an issue. Look back at our rules here. In this function, in our linear function, x is month. And in this function, x is years. I have to make an adjustment. All right. I need to fix my x's, so to say, so that they're both using the same unit of time. Right. So I could multiply 345.84 times 12 and use that value. So that's how much I'll pay each year. Or I can divide my exponent by 12. The value of the car. Either way, you need to make an adjustment so that we're using the same unit of time for each of the x variables because they're on the same graph. We use different units of time. I'm just going to divide this one by 12. That's easier. And then let's go month, 60. Right. So look at this. The blue line represents our financing, right? This is not doing what it's supposed to do. What did I do wrong? Their value. Oh. Okay. Yeah, there you go. No, a lot. 9,000. Okay, never mind. Okay. Okay. 60 months is 5 years. That's right, number 5. Look at what happened here. In this case, where you put $5,000 down, you actually save the depreciation. This is why being able to put money down when you buy a car is a good thing. You don't always have to put money down. You can finance the entire value of the car. However, if we adjust it to that, things change. Right? Plus this payment's going to be. So at this level, right, it takes 26 months, a little over 2 years, and be upside down if you finance the entire value of the car. Right? But again, the monthly payment's going to change, things are going to be a little different. And the things at play which we didn't consider, so I'm not going to get into that. Once again, the value of saving a little bit of money to put money down, that works out for your best interest. Well, you can. That's good. Break some costs with your car dealership. Take money down on that car so you can not be upside down on your loan. Right? Anywho, that example. Any questions? No? All right. So last thing, that's not what I wanted. Today's discussion board. All right. We're looking at penicillin. All right. So, on average, this penicillin will be broken down in the blood so that in 1 hour after injection, only 60% will remain active. So, this patient is given an injection of 300 milligrams of penicillin. You need to write the rule. I equals A times P to the X. And use the rule to complete the table. And then answer approximately how much time will it take for there to be only 150 milligrams of active one left. All right, so it's similar to the first example we did.